Okay. Thank you very much. Thank you, Michelle, for the invitation. A very nice introduction. Thanks. Yeah, so today my topic is beyond positivity. So I will briefly give a brief review, and so that we will have more context in which how this subject fits into the broader scope. But mostly I'm going to talk about a recent paper that I had put out with my group here, with including Laurentio Rodina, who is a postdoc, Awady, who is now a PhD student in Northeastern, and two excellent undergraduate students, Yuan Jian and Zhengwen. So in this talk, I'm going to focus on what I call the space of healthy effective field theories. So let me just clarify, what do I mean by space? So here, space, sense in general, when we think about an effective field theory, we think about a Lagrangian in which you have higher order irrelevant operators, which are parameterized by various coefficients. So here, by space, I mean the space for these coefficients. So, so then what do I mean by healthy? So it means that I'm assuming that this effective field theory it descends from something that is consistent in the UV. So it has a UV completion, where here consistency is defined by that the UV theory is unitary and it's Lorentz invariance. So this is the context that we're discussing. Now, why are we interested in this? Well, first of all, of course, we like to note from a first principle point of view just how large these effective field theory operators corrections can be, which is parameterized by the coefficient. And furthermore, if we know that if we know a precise boundary of this space, then it will be interesting to know what are the theories that actually populate the boundary. And usually when we find theories that are actually on the boundary, these usually in turn indicate the optimality of the initial assumptions, meaning that since there are a consistent theory that sits there, that means that we've used all of our consistent conditions completely to dictate what the correct space is. And finally, one of the main motivations, in particular to discuss this in the context of gravitational theory, is that we want to use the effective field theory as an avatar to parameterize whatever the UV completion of quantum gravity may be. And for example, so if the theory is, for example, if you have perturbative string theory, then the perturbative string theory represents a particular point in this space because it gives a set of precise coefficients. So we will work with the effective on-shell 2-to-2 scattering amplitude. This will be our main tool here. And the idea is that whatever UV degrees of freedom you have in the infrared, you just have basically an effective scattering amplitude, where the scattering amplitude essentially takes the structure of you have various massless singularities, and then you have a polynomial expansions in terms of your Mandelstam variables. Now, of course, the reason that we want to work with using amplitude is because, first of all, this is a well-defined physical observable. Therefore, it's free of various ambiguities that might associate with, for example, field redefinitions and, for example, gauge symmetry. Now, the other reason is that the Wilson coefficients in this language can be defined analytically from the observable. So in here, in our original format, where we're discussing in terms of terms in the Lagrangian, as you know that we can integrate by parts, we can do field redefinition. But here we can have a more precise analytic definition of these coefficients from the amplitude, IR amplitude analytically. And in particular, if I write these coefficients in this form, where I have a polynomial expansion, since it's a polynomial expansion, I can pick out these coefficients by, for example, I can do a counter integral of my IR amplitude with, and I view it as a function on the S plane, and then encircle origin, which picks out the correct powers of S from this, and then doing derivative expansion in T, I can precisely pick out what my coefficient is. Now, one of the main toolkit is, or one of the main point of this whole approach is that we have control on the analytic continuation from the origin, which means that we know that in the origin or in the origin in the complex S plane, which is low energy, we know that the amplitude takes this form. Now we would like to understand what are the singularities that appear away from the origin, and therefore we want to do analytic continuation. And generically, we have various good arguments for understanding what singularity might lie beyond the complex S-plane. Of course, as most of you have heard before, that there is some subtlety associated with whether or not you take into a massless branch cuts. And for example, so there's various ways of doing analytic continuation from the origin. So I'm showing some various contours that have been mentioned in the literature. For example, if we do not have any massless branch cuts, or in other words, there's some reason that we can suppress the massless loop by, for example, the massless degrees of freedom are perturbatively interacting, and therefore we can perturbatively suppress them, then the analytic continuation is pretty straightforward. You just do a continuation from this contour onto this contour, where the places where you have non-trivial singularity might be just on the real axis and potentially infinity. But if you have massless branch cuts, for example, then you might want to redefine what you mean by your Wilson coefficient by shifting the original contour off the real axis, or for example, consider another set of contour where you're actually integrating over near the origin, you're actually integrating over arc. Therefore, you're introducing some energy dependence here. So there's various ways where we can take into account where we can utilize our understanding about the analytic property of the amplitude and continue away from the origin. Now, one of the modern incarnation of this of the approach is really motivated from the CFT and the modular bootstrap, which just to remind you, that in the CFT bootstrap, you basically have your observable, you have a particular representation of your observable. Here you have, for example, OPE expansion in one channel, and then you have another representation of exactly the same observable, but then the point is that these two representation have an overlapping radius of convergence, and therefore the fact that they can actually be equal to each other imposes a non-trivial constraint on your observable, and therefore on whatever physical quantity you can extract from it. Similar statement is for the modular bootstrap, where the observable at hand is the partition function, and the partition function can be defined on two equivalent toruses, but their representation is going to be distinct, and therefore this also imposes non-trivial constraint on your spectrum. So motivated by this, the modern incarnation is to again, we use the fact that we have analytic control of our amplitude, therefore we can have a particular representation of our EFT couplings. For example, if I use this most naive analytic continuation where I do not have any massless cuts coming in, then my coefficient has a very well-defined representation. It's represented in an infinite sum of terms that contribute from massive pole contribution and terms that come from the cuts. So I have a particular representation for my couplings. Then I just impose again that there's a crossing symmetry, or there's permutation invariance if I have four identical scalar, which means that there's linear relations between my couplings. And so by combining these two, I can impose constraints on my space. Now, actually, of course, there's various different ways you can, so here I'm using a particular, so what we call fixed T dispersion relation, and then impose crossing symmetry. You can turn this around and first impose crossing symmetry, and then impose locality as a further constraint. So this will be the manifest crossing bootstrap, but I won't talk about it. But for people who are interested, you can look at these sets of papers. So let me just be a little bit more precise about this approach, which actually is already mentioned in various talks in this series, which is various fantastic talks. So the point is that these Wilson coefficients have a particular dispersive representation, where you're basically expanding on particular basis. So here the basis is what we call Gegenbauer polynomials. So this is like partial wave expansion in 4 dimensions. And then we impose crossing symmetry. Now, as I mentioned, so there's various talks on this in various contexts, including the inclusion of massless cuts, and including, for example, in the gravitational context, how to use this. And you in these various slides, you see these graphs that are being plotted out, where we can deduce that there's that the couplings space, the space of allowed couplings, are constrained to a finite region. Now, the thing I want to draw your attention to is that these couplings, so this is G tilde, I didn't mention what G tilde is. G tilde is actually a ratio of some particular Wilson coefficient against another Wilson coefficient. And here the ratio is actually more precise. So here you see that. So you see that in all of these results that have been derived so far, these are results that constrains the ratio of these Wilson coefficients. Okay. In other words, the constraints are in a sense projective. So that means that if you rescale all the Wilson coefficients by infinity, as long as you rescale, but these coefficients are held fixed, then it still lives within these region. Of course, if you scale the Wilson coefficients by infinity, then the EFT doesn't make sense anymore. You're already way outside the regime of valid EFT. But the point is that the bounds that are derived using this kind of format is basically projective bounds. Now, to be more precise, why are they projective bounds? Well, the reason is because when we're trying to do this bootstrap, really what you're implementing is you're implementing that these expansion parameters. So you're only imposing that these expansion parameters, or the partial wave amplitude in some sense, are positive. Okay, so this is what I mean by positivity in my title. So it's really using that this is positive. So if you have some solution which satisfy this particular dispersive representation with a particular spectrum, for example, and you already satisfy the crossing equation, which again is just a linear equation, then obviously you can just take this solution and rescale everybody uniformly and you still get a solution. Okay, so that's why, in particular, that's why the bounds that we obtain in this format is in a sense projective. Okay. However, we know that just from unitarity alone, we know that these coefficients, which comes from the imaginary part of your amplitude, is actually bounded from above. Okay, so this is a standard scattering amplitude. The standard quantum field theory textbook. We know that we can, if we expand our amplitude on partial waves, then the fact that the amplitude is unitary means that these partial wave amplitude, in particular the imaginary part, are bounded. Okay, and so basically we're usually using just the fact that the imaginary part is positive. But now we would like to ask, is it possible to actually now impose that they have an upper bound? Because as you see, once you have an upper bound, then everything is not projected, because you cannot arbitrarily rescale these coefficients anymore, because if you rescale it, you violate these bounds, that this is not a valid solution. Okay, so basically the main part of this talk is that I would like to implement, find a way to actually implement this upper bound. Okay, now what would you expect? Well, you would expect that if you impose this upper bound, then it will mean that you will impose the upper bound on your Wilson coefficients. In particular, you would expect, because on general, if we look at the available effective field theories around us, in general, we see that the couplings, when it's weighted by the appropriate cutoff, is of order 1, with some loop counting factor, normalized by particular loop counting factor is order 1. So the fact that the operator, these coefficients are bounded by order 1 is what we should expect if we actually successfully implement this bound. So this is what is usually called the naive dimension analysis. Now, just as a very like a standard example, so if we take the chiral Lagrangian, which is an effective field theory, then in this context, the dimensionless quartet coupling, the 4-pion coupling, now it grows with energy as the energy over f, the pion decay constant square. Okay, so this is the usually quadratic growth of the coupling. Now, if this remains an effective field theory under the cutoff lambda QCD, or more precisely, if lambda QCD is the correct cutoff, then we expect that this effective field theory to be still valid roughly right before the lambda QCD. That will mean that we should just put lambda QCD in here. Then this coupling should still be bounded by 1, which in turn gives a relationship between the cutoff and your pion decay constant. And as you know, that roughly speaking, this bound is respected. And so this is an example of the statement that you expect your EFT coupling, when appropriately weighted by the precise cutoff, should be of ordered 1. So this is the precise statement. And I like to emphasize that actually to try to prove this statement, to try to prove this naive dimension analysis was one of the original motivations or one of the original goals of the CFD bootstrap. And in particular, I just quote this: is there an upper bound in the interaction strength in any relativistic quantum field? It was the original question that was posed in this paper, which in turn reformulate this as a statement about CFT or OPE coefficients, which then they try to bound, give upper bounds on OPE coefficients. Okay, good. So great. So if we can actually systematically introduce this kind of upper bound on the partial wave, then we can and have a better understanding of this type of bound, this type of non-projective bound on your EFT coefficient. So let's just do it. Let's just directly do a very naive. Let's just do the most naive thing possible. So let's just do the strict forward limit exercise. So then see what would be if this is actually possible. So we know that in the strict forward limit, so that means that I'm just looking at, so remember in my parameterization, which I defined here, there's a K and a Q on my Wilson coefficient. The K basically measure what is the mass dimension because it's the total degree of Mandelstam, and Q is the degree of T. So in a sense, since T is related to your scattering angles, is basically Q is measuring how far you're away from the forward limit. Okay, so let's try to do a very simple, so let's just make things simple. Let's just do just the strict forward limit, which means I'm taking Q to be 0. Then again, this GK0 has a very well-defined analytic expression in terms of my scattering amplitude. Then using, again, contour deformations, I can relate this to the spectral parameter when you're expanding the imaginary part on your partial waves. And basically, it's just an integral from m squared to infinity. So now, the important thing is that now this spectral parameter is not only positive, it's bounded above by 2. Okay, so let's just introduce this bound here and then see what this says about our GK0. Of course, you can for most of you can already see what the problem is. So I mean, but just to use this opportunity to introduce some notation, so I'm going to introduce this dimensionless ratio m squared over s, where m squared is my cutoff over s. So this is dimensionless. So this integral can be rewritten in this form because this is the form that we will use later on. Because this is just a change of variable that changes from s to a dimensionless quantity. Okay, good. So we go ahead. So we have this representation which tells you what the GK0 or what the forward limit couplings are. And since rho is bounded above by 2, so naively you can just take rho, replace it by 2, and just do this integral. If we do this integral, fine, we'll get this number here. But now you immediately see the problem. The problem is that you need to sum over infinite number of spins. Okay, there's an infinite number of spin partial waves. Okay, and these partial waves are actually even these partial waves, each one has actually a factor of L, 2L plus 1 factor sitting in front. So this sum is formally divergent. Okay, so you're not going to get any upper bound. So the naive way of doing this, you're not going to get anything. You're just going to get infinity, and therefore you're not going to get any upper bound. Okay, of course. So this is coming from, and so for generically, you're going to have infinite number of spin just because of the fact that you have loop effects. So as we know that if you go to loop, the discontinuities that you have in your loop will generate an infinite number of different spin partial waves. So this for generic theory, these are indeed an infinite sum. However, for generic theories, we know that these spinning, let me call this spinning spectral functions, are actually dominated at low spin, even though there's an infinite spin, but actually at high spins, they are suppressed. So for example, if we take a massive scalar loop, which means that they have some light states coupling to a massive scalar, and massive scalar is in a loop, we can compute its discontinuity, and then the expanded discontinuity on the partial waves for various degrees of partial wave for some fixed s, it takes this form. So you can see it's highly suppressed as L goes to large L. And similarly, for example, if you look for tree level UV completion of this, the tree level string theory as your UV completion, then you can take each level n. So this is the string resonance level, and then look at the coefficient you have for your string scattering amplitude for each level. And you see indeed for the leading coefficient, it's always the spin 0, and then there's a huge gap between spin 1, spin 2, and then further more. Okay, so it's always dominated by the lowest spin. Okay, so that means that in principle, these if you incorporate the low spin dominance, then this upper bound might not be divergent. So the question is, how do you implement this low spin dominance? So how do you, so we know that for generic theories, these functions are actually dominated by low spin. I'm using low spin dominance, which is now a coined term for this phenomenon. Now, I'm going to say that to a certain degree, the low spin dominance can be inferred from crossing. Okay, so the reason I put a certain degree in quotation marks is because that it is by far not, it does not fully explain this phenomenon. So for example, the low spin dominance that was first presented by in this work by Zvi, Demetrios, and Sasha, they already incorporated the null constraints, and they still find that the generic theory is populating in a very narrow space. Oh, actually, yes, I have your picture here, where you see that the generic theory is actually populating a very tiny region here. Okay, so that's why I say that to a certain degree, it can be inferred, but it's still very far because of this fact that even when crossing is incorporated, you still find that the known theories are in a very small island. However, from crossing, you can still infer some degree of null constraints. And in fact, as you will see, that just using crossing, this will give us sufficient low spin dominance to give us an upper bound on these Wilson coefficients. So, so what is crossing symmetry? So once again, as I mentioned previous, crossing symmetry is telling you that, for example, these Wilson coefficients, they're actually not all independent. They're linearly related because of crossing symmetry. So usually we call this null constraints, which means that linear combinations of Wilson coefficients will be 0 because of this symmetry. Okay, so we know that there's linear combinations of these, and of course, the linear combination of Wilson coefficient, in order for it to make sense, it must be of the same derivative order. So for example, here I'm at what I call N8, which means I'm doing k equals 8 or 16 derivative order. You're going to have two separate null constraints. Now, so the null constraints are parameterized by the derivative order. Now, of course, at the same time, these Wilson coefficients has a dispersive representation, right? So that means that if you plug in the dispersive representation for these Wilson coefficients, then you're going to get something that looks like this. The null constraint can be expressed in terms of sum over all of the states multiplied by a polynomial, where the polynomial is a function of your spin. Okay, and this is the spectral parameter that was mentioned before. So I can define this as the average because it's weighted by the mass of its the mass of this state. Therefore, the statement is that the average multiplied by this polynomial must be 0. Okay, so this is what the null constraint means. So if you draw this polynomial generic, it will look like this. So you immediately see that as you go to higher spins, this polynomial, because of the simple fact that there's a finite polynomial, that this polynomial is positive, right? So, and it's positive with a large value here, okay? So that means that these spectral parameters cannot be arbitrarily large, because then if it's arbitrarily large, then this is impossible to cancel against the part that is negative to give you something that is 0, which is implied by crossing symmetry. And in fact, you can derive ratio bounds between them. So for example, the higher spin weighted normalized by the spin 2 partial wave is given by something that is inverse to L to the 4 polynomial, which means that the higher spins is heavily suppressed. Okay, so once again, the important point is that you already see this kind of high spin suppression just from the implementation of crossing symmetry. Good. Therefore, this is the proposal. And this is what I would like to show you, is that we can now actually derive precisely these upper bounds that I mentioned before on these Wilson coefficients by incorporating this upper limit of your partial wave and implementing this into this crossing symmetric bootstrap problem. Okay, but this I frame it as a question, but of course usually when you frame it as a question, from the tone you already know what the answer is. Okay, so let's go ahead and see how this is done. So I'm going to use a very nice fact that is actually a very nice property of this dispersion representation of your couplings that is actually mentioned in various work already discussed in this series of lecture, is that this dispersive representation is actually very similar, and in fact, in some sense, is exactly corresponds to what is called a moment problem or a moment representation. So let's take a look. So again, let's first look at the forward limit, just to simplify things. So the forward limit Wilson coefficient is given by a particular representation that looks like this. Okay, so you have a z, and this is some function rho of z, where you know that this rho of z is positive, multiplying by some kth power, which tells you which is related to which derivative order you're interested in. And again, this m is your cutoff. Okay, so a particular set of the spectral function gives you a particular set of Wilson coefficient. Now this formula, if I forget about these boring constants here, then this formula looks, if I clean this up, then this looks similar to this formula, right? Where I have some coefficients ak is given by some rho of z. Rho of z is just some positive function. I should mention that it's a positive function in this integration regime. And then that's it. So the question, which is usually framed the moment problem, is it asks you to determine what is the condition. Okay, what condition must these coefficient ak satisfy that guarantees a solution exists? In other words, that guarantees, so what are the conditions on ak such that ak can be represented in this form with rho z bigger than 0? So this is in mathematics what is called the moment problem. And in particular, the moment problem are defined with different integration regimes. So in this particular 0 to 1, which is our physical problem, this is called the Hausdorff moment problem. The solution to this moment problem is related to what is called the Hankel matrix, which is you just take your coupling. So again, if you see this AK, you should remind yourself that these are the Wilson coefficients. So you just organize your coefficients into this symmetric matrix, and then demand that this symmetric matrix is positive semi-definite. And that's the solution. Again, what does a solution mean? It means that once you satisfy that this Hankel matrix is positive semi-definite, then that guarantees you that there is a solution. If I map it to this space, then that means that this is a valid, healthy EFT Wilson coefficient. Okay, so there's various, this was discussed in various work before, and I believe that Francesco also mentioned this in his lecture a year back. Now, why Hankel matrix? So actually, I want to just emphasize why does Hankel matrix pop out? Because this will motivate us to know how we're going to incorporate this upper bound. The reason that Hankel matrix pop out is, so let's just say if you have a set of vectors where this set of vector, that this set of vector is given by a positive sum of something that looks like moments. Okay, it's xi squared to xid. The reason I write these things in terms of moments is because of the fact that my AK is some Z to the K power. So that's why I use moments. Then if this is written in this form, then you can see, I mean, if you just stare at it a little bit harder, then you can see that this so-called Hankel matrix is actually nothing but just the sum of your moment vector times the transpose. Okay, this is nothing but this. Okay, so therefore, if your y, these vectors are given by a positive sum of these moments, then your Hankel matrix must take this form. Then that means that if you take the inner product of this matrix from the left and from the right by any vector, it will always be positive. And for those, this is what we learned in our undergrad linear algebra, that means that this matrix is positive semi-definite. Okay. Now, why do I want to discuss this? Well, it's because then, as we mentioned, that we're going to be interested. So I want to emphasize we're going to be interested in the boundary of this space. So the boundary, since this is an inequality, so that means that the boundary is when this equality is equal to 0. So when this equality is equal to 0, that means that this Hankel matrix is, of course, since this is a sum of vectors times its transpose, that means that this matrix has finite rank. So in other words, the boundary of your space is the space where you have a solution which actually had finite number of states. That's the important point that I want to emphasize. Okay, so let's keep this in mind. Now we're going to go to the more physical problem, or the problem that we have at hand, which is, again, I have this forward limit dispersive representation of my forward limit coupling, but now I want to put not just rho is bigger than 0, but rho is bigger than 0 and smaller than 2. Okay, so again, I translate back into my toy model, which is the usual moment problem. Now my moment has an upper bound on my rho coefficient, and this is what is called the L moment problem, which is also well studied and since the 1930s. Basically, the boundary of the moment the problem is given by the positivity of Hankel matrix for these couplings. The boundary for the L moment problem is given by the positivity of the Hankel matrix for what I call BC coefficients, which are related to this A coefficient by this exponential map. Okay, this is not important. The important thing is what is actually the boundary solution. So the boundary solution, for example, so let me just take two coefficients, AK1 and AK2. Then the boundary coefficient is basically just take this. So this is the space that you get. And notice that the boundary here I give you, so this is the boundary parameter. This is how you parameterize the boundary. And there's a one-dimension parameter here. But an important thing is that what is the solution? So the solution for the lower boundary is that it's a step function. Okay, which means that rho is basically L for anything between 0 and m, for some interval between 0 and m. And then for the upper boundary, it's the rho is given by L for m to 1. Okay, so this is the solution. You plug this into here, and then you get these two boundaries. Okay, so we have the boundary solution. So in the original moment problem, the boundary solutions are finite states. Here, the boundary solution is finite segments. Okay, great. Now if I look at this equation and this equation, you see that this is very similar, except that there's only one difference, and the difference is that here I have a sum because I need to sum over infinite number of partial waves contribution. Now, if we compare these two, so the fact that I need to do infinite number of sum means that we need to do what is called a Minkowski sum. Okay, so this now I'm putting back the full Q dependence. So now it's not just some L, the L polynomial is going to have Q dependence as well. But an important point is it's essentially infinite sum of the original moment problem, which we call the Minkowski sum. So Minkowski sum is very simple. It's just basically if you have, for example, here I do a Minkowski sum of two disks. So it's basically you're just summing the Minkowski sum of two spaces is just the sum of all vectors in these two spaces. Okay, so for example, I have this vector here in A and another vector on the boundary for B. Then the sum of this vector and this boundary vector on B gives me a point here. So this is the sum. So this light blue region is the Minkowski sum of this B disk and A disk. Okay, so this is the Minkowski sum. So since I already told you that these L moment problem has an area that looks like this, and of course it's higher dimension generalization. Therefore, if you have infinite sum of these L moment problem, then I need to compute an infinite number of these, and then compute their Minkowski sum. Now you might think that this is very complicated, but if you look at this, then you realize an important thing is that the boundary of the Minkowski sum is actually the Minkowski sum of the individual boundary. Okay, so this is the boundary of A, this is the boundary of B. The Minkowski sum of these two boundaries give this dark line here. Okay, so here we see that if we want to have the boundary of our Minkowski sum, we can just take the boundary of the individual area and then take the Minkowski sum of both of them. Of course, this gives you two boundaries. Then you need to extremize the two to find the right solution. Okay, so this is just an example of taking two of the L moment problem, and then I do a Minkowski sum. So basically, what you do is you already know what the boundary. That's why I emphasize on the boundary of the individual L moment problem is, and then when you combine them, that means that it combined. That means that it combined. So originally, so for these are the boundaries of the individual, and then I do a linear combination. Then I extremize to get a particular coefficient for the linear combination that actually extremizes the boundary, which you can just directly do using the usual Lagrange method. And this is the form that you will get here. And this gives you so this is the result of your Minkowski sum. Okay. Good. So this is just a sum of two pieces, but in our, yes, I guess, Francesco, do you have a question?
Yeah, can you hear me?
Yes.
Yeah. Now, one question. In this plot, the projective bound would not be a
Yeah, so the projective bound will be like the slope. So it will be like a one-dimension slope. So sorry, so it will be the slope, and therefore it's a one-dimension. So it's the value of the slope. And sorry, and then of course, I guess I didn't put it here, but then here, because I'm sorry, here I guess L is put to 1 here. So if you actually put L to infinity, then this thing blows up into a cone. Yeah, so yeah, good. So remember that. So this is really so if I blow this L up to infinity, which is the upper bound, which is the usual projective thing, then this object here blows up into a cone. Yeah, is that okay? Okay, thank you. Right, so this was summing two of these objects. Of course, now I need to sum 3, I need to sum 4, and then you can sum infinite, and then you take the analytic continue to infinity, and this is the region that you will get. So notice that this upper bound now tends to infinity, but you see you have a non-trivial lower bound. So the lower boundary actually doesn't go to infinity. Okay, and in fact, when you implement the null constraint, the upper boundary will actually doesn't matter because the null constraint just cut over a lower boundary. So this is the way that we're going to do this. So you basically have a moment problem. For each spin, you have a moment problem. We know what the solution for the moment problem is for any one of these spins. And then we just systematically do the Minkowski sum of these areas to get what are these boundaries. So once we have these boundaries, we can just intersect it with crossing symmetry, and then that will give us non-trivial bounds. So here is an example. So let's consider, first let's consider what we call equal case space, which means that we're looking at Wilson coefficients of the same derivative order. So for example, if we look at the G42 and G40, this is the area that we would have. And then we intersect it with what is required by the null constraint, because G42 is related to, there's a relation between the coupling, and then you get an upper bound. So now we see that G40, again, weighted by 4 pi squared, indeed has the correct result that is actually of order 1. And you can do the same thing for k equals 5. So now we're getting all these various different results for different Wilson coefficients. You can, for example, here we're considered this is actually a 3 dimensions. This is actually a 2-dimension slice of a 3-dimension space with the k equals 6 constraints. And here we get usually, I mean, you always get two-sided bounds because you already know that these are positive, but now you have an upper bound. Okay. Now, there's actually a better way to do these things, which allows us to actually derive a bound which is valid for arbitrary k, so arbitrary derivative order. And that is that first of all, you start you start with your dispersive representation, but then for the other part, you actually instead of for another coordinate, instead of using instead of choosing another Wilson coefficient as your coordinate, you actually just choose the linear combination of Wilson coefficients and coordinate. So then you just choose a null constraint as your coordinate. And therefore, then once you plot out the region, then the intersection at the 0 axis directly gives you the bound. So for example, now using this, because now this is, you can actually do things where your null constraints is of different derivative order compared to your Wilson coefficients. So for example, since my first null constraint actually starts at k equals 4, but now using this, I can now bound G to 0, which has an upper bound of 1.58. And actually, this matches with a numerical result that was done for G20, which was done in this paper here, which exactly, so we reproduced this numerical result analytically. So of course, not only this, we can do this for any k. For example, we can do it to G31, which G31 doesn't have to be positive, so we actually have a lower bound and the upper bound. And we can also consider 2-dimension spaces. Okay, so this is strict G31, G20 spaces, and we give the precise boundaries of this space. And just as a sanity check, we actually try to do this using linear programming. So basically what it does is it uses a scanning over the grid. It discretizes the problem and it scans over the grid to maximize these couplings. And you can see that this matches very well with the numerical approach. Okay, so we have these precise bounds. So this is the precise upper and lower bounds for G20 and G31. So as I mentioned, I can have do this for arbitrary k. So I'd like to present you with our result for arbitrary k. So you notice that for any k, it's actually suppressed. So it's actually not order 1. So it's better than order 1. So this is one of the main points, is that it's actually better than order 1. So as you see that as you go to higher and higher derivative order, the Wilson coefficient is bounded by above, but it's actually approaching 0 because there's this 1/k factor here. So this is interesting. So not only is the Wilson coefficient bounded by 1, but it actually has a combinatoric factor. For us here, so far we were getting just a single null constraints. We're getting a 1/k suppression. Now, of course, we can match this to known theory. So for example, let me just take a scalar box, just a scale. So this will correspond to a massive scalar in the loop. I can compute its Wilson coefficients, and then I can compare, and you can see that these are the bounds that you get. So this blue dot is the bound that you have, and the green dot is actually the result from the scalar box. So it actually it matches with this blue dot. It matches here, but actually at large k, the scalar falls off much faster. It falls off by this 1/k factorial. So generically, if you compute this from Feynman diagrams, then Feynman diagrams actually satisfy this bound precisely because of these combinatoric factors. Okay, these combinatoric comes from Feynman diagrams. But here, yeah. So, but here we show that it satisfies this bound. Yes, Francesco. I think you're muted. Oh, sorry. Is there some reason I couldn't hear you?
Can you hear me now?
Oh yeah, now.
Bluetooth airplay. No, so my question is this: at the beginning, you assume that the theory is weakly coupled because your dispersive integral goes from m² to infinity, right?
You mean that that there's no log running for the massless loop?
Exactly. This is what I'm.
Yeah, these are bounds. Yeah, these are bounds where I'm deriving that there's a. Yeah, these are bounds where I'm not incorporating the massless loop. In other words, I'm assuming that the radiative corrections are suppressible.
Exactly.
Yeah,
This is, I'm confused because then you find these upper bounds are of order G 4 pi, right? In units, is it something order 1 times 4 pi. So it's they appear to be at the edge of what I mean. At the edge
yeah,
of
you mean the spot? You mean the spot?
No, I was thinking of the method in general. The fact that.
Okay.
But yeah, I'm surprising that this plot comes like this because perhaps.
Yeah, the plot is actually a fake in some sense because I have to normalize what I mean by lambda.
I see.
So it's actually I'm tuning this such that actually the lambda hits the first, so it's actually below the first thing, and then I'm just seeing how the remaining things actually compare to the slope. So once it's saturated, once it's satisfied the first allowed bound, then I look at how the remaining higher derivative terms are actually follows. Okay. Yeah, because there's this coupling, as you mentioned. Yeah, exactly. So this would be the coupling that you're talking about, that I'm essentially assuming. So this coupling cannot be large, but how not large is it when I'm plotting this? So I'm just, yeah.
Okay, and this, I mean, the fact that you factor out lambda does not reduce to the projective bounds. You're saying there is still something more to it, right? Anyway, yeah, go ahead. Now I think I understood your comment. I will think about it and
okay.
Perhaps come back to it. Thanks.
Okay, thank you. Right. Right. So this is what we've done for the scalar theory. Of course, you can straightforwardly do this for a gravitational theory. So let me just because of time, I'm just going to flash some results. So, for example, for gravitational theories. So here, of course, as been mentioned, as been discussed in various previous lectures, that when you're talking about gravitational bounds, there's always the 4-limit t-pole singularity, which you need to take into account somehow. So here we're just looking at operators which are not polluted by the t-pole, which are operators which are beyond two derivatives. So these are higher derivative operators. So these do not satisfy. These do not suffer from the t-poles, and you can get something similar because these are basically the same approach that you would get. Of course, if you think about it, it's not really that impressive, because of course we need to, at the end of the day, put back where M Planck is. So if I assume that I'm still perturbative in M Planck, and only non-perturbative in the massive states, then that means that I will have the usual 1/m Planck square associated with tree-level coupling. But then that means that if I need to put, since my precise bound is of this point, I need to have this ratio of M Planck squares over M square. Then this ratio can be arbitrarily large. So the M Planck square over your UV cutoff can be arbitrary. There can be an arbitrarily large separation, and then therefore this upper bound will go away in that scenario. Okay, but still you can irrespective of so to really have a proper control related to the M Planck, we really should need to do this analysis with when the graviton pole is taken into account. Okay, so now I guess I have 8 minutes left. So let me just briefly mention some slightly tangential direction, which is that, let me just go back to my first slide. So in the first slide, I was talking about the space of healthy effective theories that descends from consistent UV completion. But actually, there's another way of saying what is healthy effective theory, which is basically in the IR, where in the IR, I can consider my effective theory, and I can consider non-trivial backgrounds on which I talk about, I consider fluctuations around it. And I can ask whether or not these fluctuations are super-luminal or not. And indeed, in the early paper, which in the early work done on this, which actually analyzed these two problems at the same time for the 4 derivative interaction. And this is the famous positivity, which really, in some sense, began the whole march which showed that from the UV, we have the usual dispersive representation, and we know that the fourth derivative term should be positive. In the IR, you also see that they also should be positive, just from the fact that you cannot have superluminal fluctuation. So it's natural to ask what happens beyond the fourth derivative interaction. And what is there any background where we can actually scatter off in which we can talk about whether or not there's superluminal fluctuations? And furthermore, if there is such a background, does the consistency conditions that you get coming from the UV actually directly matches with those of the IR, or actually are much stronger than the IR? So this is an interesting question that one can pose. The other question is actually that if we actually analyze this kind of if we have non-trivial backgrounds in which we can fluctuate and analyze superluminal, then this kind of analysis will basically be free of various discussion that actually already been brought up by Francesco, or that we've mentioned about whether or not the amplitude is bounded at large S. Fixed a small t, or whether or not there's t-pole, whether or not there's friendship. This is not an S matrix analyticity argument. This is just take your effective field theory on face value, consider a background, and then consider fluctuation. So let me just briefly flash. So I just go real fast. So let me just give a quick review of what happened in the original discussion in the original work. So let's just take again the fourth derivative interaction theory. Forget about the higher derivative terms. The reason you can forget about them is because if you consider the scattering sorry, not scattering, if you consider this theory in the background where you have a constant vector. So we're going to consider a non-Lorentz invariant background for phi is going to be C mu X mu. So it's obviously a solution to the classical equation of motion just from the nature that it has higher derivative. I'm going to expand around this background. Then the equation of motion for this fluctuation mode is going to take this form. Now, what is so deadly about this form? Well, let's consider a particular background. So let's consider a space-like background, just C mu equals 0, 1, 1, 1. Then this equation of motion becomes partial t squared, and then you have this this combination here, or this combination, I'm just going to call it V squared. Okay. So you're going to have this form, but now you see that you're going to have the problem with superluminality, because that now you can do a Lorentz boost on this form. Just do a change of coordinates, for example, in the X direction. Then after the Lorentz boost, the time derivative part is going to have this combination where beta is the usual V over C. Then you immediately see that if V is greater than 1, then you're going to find some frame of beta, in particular 1 over V, such that the time derivative drops out. There's no time derivative anymore. And in that frame, everything becomes instantaneous. Okay. And therefore, in that case, now you can no longer set up an initial value problem. Okay, so this says, so when does V become greater than 1? Remember, this was V squared. So V greater than 1 is precisely when C2 is smaller than 0, when it violates the positivity bound. Okay. Actually, it's not just here in this frame. You can also do it for the other one. So that if you actually do it for example, a time-like background, then you can take it. Then the differential the equation of motion will take this form, and you get exactly the same thing, because now your velocity is 1 over 1 plus 4c2. Again, V greater than 1 corresponds to C2 smaller than 0. Okay. Now, we would like to consider now what happens now in this case. What happens if you actually consider the higher derivative terms? Well, because of the fact that this is only linear in X, therefore the higher derivative term, the higher derivative term actually doesn't contribute to this background. But we know that we can just use some kind of plane wave solution. So if we consider phi of X as C mu X mu, where C is actually null-like, then this will be a solution to your equation. This will once again be a well-defined solution to your classical equation of motion for any derivative order that you incorporate. So for example, let's take this kind of effective action. Okay, and we do again the similar analysis, and then we consider the equation of motion for some particular fluctuation phi. So just for convenience, I'm going to consider phi also in propagating in some particular direction. So if my C is extended along the Z direction, I can let my phi be propagating along the X direction. then the dispersion relation for my omega is going to take this form. Okay, so for example, again, the absence of superluminality then requires that this combination has to be bigger than 0. Okay, now C and omega, C is just your background and omega is just your coefficient. So both of these things have nothing to do with your cutoff, which is M. So actually C times omega in principle can be arbitrarily large and the EFT is still valid. Okay, of course, whether or not this series convergent is another question. Okay, so let's just, for example, let's just truncate to the to S square order. So we have basically a very simple equation: C2 minus C4 plus C6 must be greater than 0. Of course, this is just a quadratic equation, so we know that it's for the condition for this to be greater than 0, for be always true, will be just that this has to be, there's no real roots. Okay, and indeed we see that this condition, which is implied for superluminality, is actually already guaranteed by the 4-limit Hankel constraint. So this is what the 4-limit Hankel constraint is. So this is already more positive than, so if the Hankel condition, if the Hankel combination is positive, then this is definitely positive. So the superluminal bound is actually weaker than the UV analysis, the UV condition. Okay. Now, of course, you can go one derivative higher. But if you go to one derivative higher, then instead we can consider the envelope by considering sweeping out the region for x, for example, between 0 and 1. And then this is the region that you will get compared to the Hankel region, which actually carves out this space. You just compared it to, I didn't do the overlap because the overlap, this is bigger than this, so you won't actually see this region at all. But if you carefully look at the numbers on your axis, you'll see that this is actually within here. Okay. But so far from our analysis, we've seen that generically, if the UV condition is that the UV constraints are satisfied, then for the cases that we've analyzed, that in the IR, the superluminal mode constraints are automatically satisfied. But as I mentioned, that the superluminal modes constraints are actually independent of the various assumptions that I mentioned in which you will use to derive the UV conditions. Now, so before ending, I would just like to do just make one final comment, which seems interesting, which is that here I'm just doing here. This is a naive convergence region for this kind of series, without taking into account what are the precise coefficients of these things. But as you already know from the previous analysis, that these coefficients actually satisfy an upper bound, and therefore the convergence region in principle should go beyond 1. And in fact, for example, if you take, for example, the string theory Wilson coefficients, and we can show that, for example, here the convergence region extends beyond 1 to 2. And if you actually look at the convergence, you look at the envelope for this constraints on when you extend the convergence region outside of 1, then you see that the region is now actually much smaller than the UV constraints. Okay, so again, this is the Hankel constraint, and this is the region that you will get by considering the envelope of this from between 0x and 2. Okay, so this is an interesting observation, and it'll be, and we are now trying to understand generically what is the precise statement about the convergent properties of this series under various assumptions when you actually incorporate the precise suppression of these UV of these Wilson coefficients. Okay, so let me just end here. So I've shown that we've been able to incorporate the upper bound on the partial waves analytically, leading to order 1 bounds on the Wilson coefficients. Of course, there's more work that we would like to do. We would like to understand. Well, first of all, it's actually, again, doing things analytically is nice because we know what's going on, but it will be more nicer to be able to come up with an algorithm which this can be done numerically, because then we can consider multiple null constraints at the same time and see how further does the space shrink. There's various extensions, of course, for example, both from the fact that actually we can redo this analysis from when the radial corrections are included, we can look at what new constraints might you find when you consider the finite T bootstrap or the finite impact parameter space bootstrap. Now, and finally, in the last 5 to 10 minutes, I mentioned this null-like background, which you can test causality in the IR. And the bounds that are derived are not subject to the usual assumptions that you would use in the derivation of the S matrix. But so far, the bounds that we derive are weaker than the bounds that you would derive from the S matrix. But however, we find that the better than expected convergence of this series expansion seems to be correlated with known theories, and it'll be interesting to know if there's something interesting behind this. So I'll stop here. Thank you very much.
Thank you.